Hey there, everybody. This video is definitely the most technical of the bunch, so you may need to watch it a few times and really read the notes that I'm generating here. We're going to start with the remainder theorem, and we want to do some definitions here. So when we're doing long division like this, the number inside we call the dividend. The number on the outside is called the divisor. The result is the quotient, and we have the remainder. So those are our parts. So if I take 16 divided by 5, and we would write it like 3, which is the quotient, plus as a mixed number. We don't normally put the plus in between there, but it's actually there with 1 over 5. Which means if I multiply both sides through by 5 to get rid of the denominators, I get that 16 is equal to 5 times 3, or 15. And then 5 times 1/5 just gives me the 1. And that gives us a general rule here, where the dividend is equal to the divisor times the quotient plus the remainder. And that's going to sort of be the basis of what we're doing. Now, the degree of the remainder is always going to be less than the divisor, meaning what's in the denominator. And so if we have that the denominator is x minus k, which is a first degree polynomial, that means that our remainder must be a constant if it has to be a degree less, because degree less than 1 is 0, and the 0 degree is a constant. So here's our theorem. And here's our function. So this is our divisor times our quotient plus the remainder, where r is no longer a function of x because it's now a constant. And when I evaluate this at k, that goes to 0. So I just end up with the remainder. And this is called the remainder theorem. So p of k equals r, where r is the remainder. Meaning I can evaluate the polynomial at that point, and that will give me the remainder when I divide the whole thing out. Factor theorem says that, let's say a polynomial f has a factor x minus k, so any polynomial. If it has a factor, it's only going to have that factor if when we evaluate it there, we get no remainder at all. Meaning remainder equals 0. And again, we're getting a little technical here. Some of the uses of the remainder in synthetic division. If the remainder is 0, there are 3 pieces of information. They're actually basically the same information. It means x minus k is a factor, meaning when x equals k. If r is 0, then x minus k is a factor. K comma 0 is an x-intercept, and it's a 0 of the function. These are all essentially saying the exact same thing, just in different forms. Oops, I was pointing to here. Sorry, I forgot to move it up. So now we have a theorem that says, let f of x be a polynomial function with rational coefficients. Rational in our purposes just means fractions. We don't have radicals as part of the coefficients of the polynomial. Then if we have an irrational 0, then its conjugate is also a 0. So right away, if we know that this is a 0, then that also is going to be 0 with the minus in there. And we're going to use that right here. So write a polynomial function with rational coefficients with 3 is one of the zeros, and 2 minus root 7 is a 0. That automatically means, by our theorem up here, that 2 plus root 7 is also going to be a 0. So to get our zeros, here we have x minus 3. It's always minus. X minus our function, or our 0 here, and x minus our 0 here. And what we're going to do is we're going to multiply all of this together. So in short work, when we multiply it all together, we end up here. I'll let you verify the work on that as part of another exercise, because you will need to do that for a test question. So given that 6 is a solution, we're going to solve this. So what we can do, since x minus 6 is now a factor, right? Again, it's minus. If that's a factor, then by the previous theorem that we had, that means if we divide out this polynomial with this here, we should get a 0 remainder, which we do. So I quickly did synthetic division here. So x minus 6 is definitely a factor. We now have 1x squared plus 6x plus 8 remaining. That I can just factor normal. And once again, this whole thing is equal to 0. So our zeros are 6, -2, and -4. Remember, it's always the opposite sign. Number 2. So we're given that this is a solution, so right away we know that 2 plus root 5 is a solution. We're going to solve this. So again, I know that this is a solution right here, which means that is a solution, so I put it at the x minus each of those, and I FOILed the whole thing out. That got me to here. Again, you can verify that. Now I'm going to take this, I'm going to divide this from that. So here's my long division. X is going to get me the x cubed, go through the long division, you end up with a 0 remainder, and that's the key here. That means that x plus 3 is another factor. So our function is going to be x plus 3 would go here, times that, which means x equals negative 3 is a 0. And that's where I got these from. So here's my overall function. Set that equal to 0, I get that, using the quadratic formula, which we already knew were solutions. And here, set that equal to 0, I get x equals negative 3. Again, I'm going to let you work those out. I don't need to walk through how to FOIL and stuff like that. So here we have what's called a rational zero test. So here we have a generic polynomial, an nth degree polynomial in this case, where all the coefficients are integers, so we're not dealing with fractional coefficients, like nice whole numbers for us. Then if there are rational zeros, then they must come in the form of plus or minus all the factors of the very end part here, and plus or minus all the factors of the lead coefficient. That's what this is saying here. So for example, here we have a 17th degree polynomial, which is insane. Here's my a sub n, here's my a sub a naught, or a sub 0. Every factor of 5, that's just going to be 1 and 5. And every factor of 4, that's 4 is a multiple of 1, 2, and 4. And so every combination is going to be here. 1 over 1, 1 over 2, 1 over 4. There they are. Then 5 over 1, 5 over 2, 5 over 4. Now it looks like there are 6 potentials, but there's actually double that because it's all plus or minus. So there's actually 12 potentials. The short of it is, what I would need to then do, which I can't do because I don't have the rest of the polynomial, is go through and do synthetic division with 1 on this polynomial. Do it with negative 1, do it with 1/2, do it with negative 1/2, and so on until I've tried all of them. It's possible, if there's a rational root, then one of them will be the solution. I'm looking for a 0 remainder. That will tell me if it's a solution to it or not. It's possible to go through all 12, by the way, and none of them work. It's just an irrational function. All right. We're going to use the remainder theorem to determine whether the function, here we are, has a factor of x minus 3. If it has a factor of x minus 3, that means when x equals 3, when I plug it into the function, I should get 0, because that's my remainder. And in this case, yes, x minus 3 is, when I plug in positive 3 into the function, I get 0. X plus 2, if it is a factor, that means when x equals negative 2 and I plug it into the function, I should also get a 0, which I did not get here. So I would conclude that x plus 2 is not a factor, whereas x minus 3 is a factor. All right, this is where it's going to be a lot of work. In fact, it's way more work than you even see here. So for number 2, we have our function. It's a 4th degree polynomial. And we're going to list all the potential rational zeros. And you can see the 6 breaks up into, is a multiple of 1, 2, 3, and 6. 2 is only of 1 and 2. So 1 over 1 is here, 1 over 2 is here. 2 over 1, 2 over 2, that's 1 again, so we don't redo it. 3 over 1, 3 over 2, and 6 over 1 is 6, and then 6 over 2 is 3 again, so we're not going to relist it. Remember, it's plus or minus all of them. So what you would need to do is go through synthetic division with 1. I didn't get a 0 remainder. I go through it with negative 1. I didn't get a 0 remainder. I go through it with positive 1/2. I did get a 0 remainder. Yay. What that tells me is this is a factor of this polynomial. So that means x minus 1/2 is a factor, and what I'm left with is the 2. Notice it started x to the 4th. When I divide it by a first power, the x minus 1/2, it drops it down a degree. So that's now 2x to the third, 6x to the second, 4x to the first, and just 12x to the 0, or just 12. I'm now going to continue with this. So I continue on negative 1/2, positive 2, negative 2, positive 3, negative 3. Negative 3, when I do synthetic division to it, will give me a 0. I'm going to let you crank those out. These are very tedious. They take a lot of time and effort to do. So you'll just have to be patient with it when you go through these. This will never equal 0. Yeah. So our only potential are right here, as far as rational solutions, rational zeros go. By the way, you want to go down till you get a quadratic, because the quadratic, you can always use the quadratic formula. That's always easy to do. Once again, when you set that equal to 0, you can't take the square root and get a real number. You'll end up with complex numbers, which we will talk about in the next video, actually. Number 3. Solve the equation. Sounds simple enough. So we're going to take all the potentials. 15 breaks down into 1, 3, 5, and 15. Those are its only factors. I have a Lie coefficient of 1, which cuts down on what I can do. Again, it looks like there are 4 to test here. There's actually 8, because it's plus or minus 1, plus or minus 3, 5, and 15. So in this case, I tried positive 1. I didn't get a 0 remainder. I do negative 1, and I do get a 0 remainder. So this now drops down to x plus 1 times, that's x, we started with 4, so it's now x cubed minus 3x squared minus 5x plus 15. You can see that there. And you would need to continue going on with the 3 and the negative 3 and the 5 and the negative 5, 15, negative 15. But I noticed in this case that I could actually factor by grouping, and it broke it up quite nicely for me. So it now ended up here. Again, you would need to continue to do synthetic division. I would just get scratch paper as you crank through these. So my solutions are negative 1, 3, and here I end up with irrational solutions, plus or minus root 5. Number 4. Find the zeros and fully factor, so we're just factoring in this case, this cubic here. Now this one is massive. The denominator is just over 1, so that's kind of nice, but 24 has a lot of factors. Plus or minus 1, 2, 3, 4, 6, 8, 12, and 24. That's a lot to test. Again, you'll just need to get some scratch paper and just crank them out. Well, I did plus or minus 1, didn't get a 0 remainder. Plus or minus 2, didn't get a 0 remainder. Plus or minus 3, minus 3 did get me a 0 remainder. And very nicely dropped it down from a cubic, a third degree, down to a second degree, and I just used the quadratic formula to find the other two. Once again, please note, they're looking for the factors, not the zeros. So this would be 2 of the zeros, and negative 3 would be the third 0. But writing it in factored form, I'm here. Remember, it's always minus, right? So x minus minus 3 is x plus 3. And then here's x minus the positive case, x minus the negative case. So there's your factors. That's a lot to process, and once again, you may have to watch this video a couple of times to kind of get the full, everything out of it that you can get out of it.